In the last section, we looked at the multiplication rule for probability in cases where we had probability of two events where it was like A and B. We use multiplication. And in this section, we're going to talk about addition and the addition rule for probability. First, we discussed the topic of when two events are called mutually exclusive. The definition is two events, A and B, are mutually exclusive when A and B cannot occur at the same time. That is, A and B have no outcomes in common. So these pictures show if A and B don't overlap with each other, then they are called mutually exclusive. They don't share any common outcomes between the two events. If they do share a common outcomes, then that would be in the overlapping area referred to with A and B, where both can occur at the same time. And so let's talk about a couple of scenarios and identify what we think would be mutually exclusive events in this case. It says determine whether the events are mutually exclusive. First one says event A is rolling a 3 on a single dice, and event B is rolling a 4 on a single dice. Can these happen at the same time if we roll the dice once? And clearly that wouldn't be the case in this instance. Since one dice roll cannot happen at the same time as the other, you can't get both 3 and 4, we say the events are mutually exclusive. On the other hand, the other two events, event A, randomly selecting a male student, versus event B, randomly selecting a nursing major. It's possible that they could both be true at the same time. Since a student can have both male and a nursing major, the two events are not considered mutually exclusive. So we look to see if events are mutually exclusive when considering the next thing about probability, which is the addition rule for probability of events A or B. The probability that events A or B will occur is given by probability A or B is equal to the probability of A plus the probability of B minus the probability of A and B. This is, in general, either whether or not they're mutually exclusive, we can take this calculation to do the probability. However, if A and B are mutually exclusive, then we could simplify this calculation to just the probability of A plus the probability of B. We don't have to consider the additional probability of A and B component. And this rule can be extended to more than just two events, 3, 4, 5. The general idea, though, is when we speak of events happening in A or B, or A or B or C, or however many events there are, the key word "or" relates to the addition of individual event probabilities. So going back to the deck of cards, 52 cards, find the probability that the card is a 4 or an ace. And so I've highlighted the 4s and the aces in this particular deck, but we can tell that it's not possible to have a card that's both. Drawing a 4 or an ace at the same time isn't really possible. So we would say that these are mutually exclusive. They don't overlap or happen at the same time. As a result, we take the probability of each and add them together. Probability of A or B is equal to the probability of A plus the probability of B. So what is the probability of each event in this case? The probability of 4 or an ace is equal to the probability of a 4 plus the probability of drawing an ace. And since there are 4 cards for each, there are 4 4s and 4 aces out of the deck of 52, the probabilities go 4 over 52 plus 4 over 52. Adding these together give us 8 over 52, which is approximately 0.154. The next example says rolling a dice. Find the probability of rolling a number less than 3 or rolling an odd number. First off, we notice the word "or," so we need to think about, can they happen at the same time? Are they mutually exclusive? In this case, the two events are not mutually exclusive. It's possible to have both at the same time. Rolling a 1 would fit the description of both less than 3 and also odd. So since they're not mutually exclusive, we'll extend our calculation to do the probability of A plus the probability of B minus the probability of A and B. And that's going to look something like this. So event A, rolling less than a 3, there are two outcomes, 1 and 2. Event B, rolling an odd number, there are three outcomes, a 1, a 3, or a 5. So A and B would be one possible outcome of just the rolling a 1. That's the number they have in common. Here's a visualization of that. The odd numbers, the less than 3, and the one number they share in common. And so to do the probability, we need to break it down like so. We take the probability of A plus probability of B minus probability of A and B. And looking up above, we know however many outcomes for each of these events. For probability of A, there's a 2 out of 6 chance, so 2 over 6, plus probability of B, which is 3 over 6, minus the probability of A and B, which there's a 1 out of 6 chance for both. And if we put this together, it gives us a 4 over 6, or approximately 0.667 chance of this occurring. Looking at this example, here it says in a big cooler there are the following drinks: 14 bottles of soda, 3 cans of soda, and 6 bottles of juice. So there's cans, there's bottles, there's soda, there's juice. There's no cans of juice, however, just cans of soda. So it mentions this person comes in and is going to choose one of the drinks at random. What's the probability that it's a can or is a juice? Well, in total, there are 14 plus 3 plus 6, so 23 possible outcomes, 23 possible choices. The probability of picking out a can, there's only 3 cans, so there's a 3 over 23 chance of selecting a can. The probability of selecting a juice, there's 6 out of 23, so 6 over 23 chance. However, the probability of both at the same time, probability of selecting a can and juice at the same time is 0, since there's no cans of juice in this particular instance. So the full calculation here, probability of a can or juice, can be broken down as the probability of choosing a can plus the probability of choosing juice. And the formula would also say that minus the probability of can and a juice at the same time. But as we noticed above, that's a 0 chance of that happening here. So another illustration here of why we don't need to include that extra part in the formula when they're mutually exclusive and cannot happen at the same time. So all we need to do is take the probability of a can, 3 out of 23, plus the probability of selecting juice, 6 over 23. Add them together to get 9 over 23. Approximately, that's 0.391 as a decimal in this case. In this example, it says a city planner surveyed 168 residents. For each, the planner recorded whether the resident owns a car and whether the resident lives alone. The results are summarized in the table below. What is the probability that the resident does not own a car or does not live alone? So we've got these groups broken down into like 2 different ways: car, no car, alone, not alone. We got to make sure to keep in mind where they overlap when we do the probabilities in this case. So first off, does not own a car. There's a group here of 43 and 96. Does not live alone. That group is mounted to the 19 and the 96 put together. And we can see the fact that they overlap. In this case, there's 96 that are in both groups at the same time. So we know that these are not mutually exclusive events in this case. So to find the probability of one group or the other, which in this case the probability that they have no car or they don't live alone, we're going to use the probability formula, probability of A plus probability of B minus the probability of A and B, which in words would look like the probability of no car plus the probability not living alone minus the probability of no car and not living alone. So to find each of these probabilities, we're going to add together the numbers for each group. For no car, that group is 43 plus 96. For not alone, that group is 19 plus 96. Divided by the total, which they told us that there's 168 in this particular survey here. But we also need to subtract the probability of no car and not alone. The group that overlaps for both is the 96 in this case. So the probability no car and not alone is 96 divided by 168. When we add and subtract these numbers together, we get 158 over 168, which is a probability of 0.940. So here's a summary of all the probability statements we've seen up till now. The topic of classical probability, empirical, or frequency probability, the range of probability values, the complementary events or the complement of an event, and now the two that we've just seen in the last two sections, the multiplication rule and the addition rule. And I'd like to highlight specifically those probabilities that we've just seen with and or involved. When it's an and probability, this event and this event happening, we use multiplication. And it depends on if it's dependent events or independent events, how we have to go about doing that. If there's the possibility of dependent events, we use the multiplication with the probability of B given A, is what we called it. However, if we know the two events are independent, then we can just straight up multiply the two probabilities together for each event. When we talked about or probabilities now, we've seen we use addition. So the probability of A or B, when they're not mutually exclusive, we have to include probability of A plus probability B minus probability of A and B. When they are mutually exclusive, they don't overlap, then we can just add the two probabilities together.